Today in this tutorial, we want to learn how to assign oxidation states or oxidation numbers. We'll get back to the difference between those at the end of this video. So we have a set of rules. The rules you do not have to regurgitate and state back, but you have to apply them. So first rule says the oxidation number of an atom in an elemental substance is 0, an atom meaning not an ion. So if we're looking at this, we would say argon, well, there's no charge. This charge would be right there, and there isn't one, so it's going to be 0. Chlorine is molecular chlorine, but it's still just the atomic form of it, and therefore it's 0. Here's a metal. We often think of metals taking a 3+ charge or some kind of positive charge. But if they did, you would see 3+, and of course you don't, so that means that it's uncharged and therefore 0. And then you got things like sulfur 8, you have phosphorus 4, but if you add 0 a bunch of times, you still get 0. So these are molecules with a single element and no charge, and therefore everything is 0. Rule number 2, and I had to fix these. So if you saw them before, they were wrong. Now, rule number 2 says the oxidation number of monoatomic ions will be equal to the ion's charge. The format's a little different, but it's the same. So here we have monoatomic ions, one element with one charge, and therefore we're going to be able to tell it what it is. The copper 2+ is going to equal to a +2. Notice how the charge has the number first and then the plus minus, whereas the oxidation state has the plus and then the number. Phosphorus 3- would be equal to -3. Potassium plus, which is a 1+, equals to a +1. And sulfur 2- is going to equal to -2. These are technically oxidation states. So even though when we think of states of matter, we think of phases, and oxidation state is the number. So it's a -3 here, it's a -2 here, etc. The rules continue. Rule number 3. This is split into a couple of things. So we're going to end up using simple algebra to figure out the oxidation state of some unknown elements. And for that, we're going to need to know a lot about hydrogen and oxygen. So hydrogen is going to be 0 in elemental form. We already covered that, so that's 0. This is what I tell my students is a zebra. It's an odd thing. It doesn't happen very often. If you have an ionic compound, it typically goes plus and then minus, and in this case, it is plus and then minus, and therefore the hydrogen is a hydride, or a 1- charge, and therefore a -1 oxidation state. However, hydrogen the rest of the time is going to be a +1. Whenever you see it in a hydrocarbon, it's a +1. Water is a +1. If it's in a polyatomic ion, it's a +1. So it's almost always +1, and we'll need that information to figure out some other things. Oxygen kind of works the same way. We know that molecular oxygen, well, that's a 0. We know that oxygen in peroxides, this is my zebra for the oxygen, you don't really see peroxides too often. It's an O2 polyatomic ion with a 2- charge. With the group of oxygen taking a 2-, each one on average would be a 1-, and therefore the oxidation state for peroxide is -1. It just doesn't happen very often. And then listed are some really, really odd ducks, so we're not too worried about them. But what I want you to understand is oxygen almost all the time is going to be a -2. So in polyatomic ions, when the oxygen is there, which are in a lot of them, they're -2. Hydrocarbons like alcohols and acids and things, it's a -2. Carbon dioxide, it's a -2. It's almost always a -2. The halogens are typically a -1. There are some rules with this. It's really based on electronegativity. Electronegativity gets bigger going to the right and up, which means fluorine is the largest. So fluorine is definitely always -1, even next to oxygen. Oxygen is the second biggest electronegative species. So halogens can kind of play a weird part. We don't typically deal with them too much. So there are more exceptions. We're going to kind of skip over them for right now. Finally, the last rule is basically that the sum of the oxidation numbers, oxidation states, for all atoms in a compound or polyatomic ion equals to the charge. So we're going to do some simple algebra, and the answer to the sum of all the oxidation numbers will equal to the charge. Each atom of each element has its own oxidation number. There is no oxidation number for a group of things. A molecule here does not have an oxidation number. A polyatomic ion doesn't have an oxidation number. It's each one. So carbon dioxide, the whole thing equals to 0 because it's a molecule. So we'll say equals 0. We know that oxygen, for the most part, takes a -2, and it does in this case. And there's 2 of them. So if you have a -2 and another -2, you have a -4 all day. The carbon can be a lot of different things. You can't just look at it and tell. And therefore, we don't know what it is, and therefore we call that X if we're in math class. Okay, solve for X. X equals to a +4. And so the oxidation state for carbon in this case is a +4. Here is something called ethane. It's similar to propane and methane. And we're going to go through the same thing. So the oxidation states for hydrogen most often are +1s. Unless it's by itself and diatomic, it is not. Unless it's a metal hydride, this is not an ionic compound and it's not the anion, so it is not. And therefore, the rest of the time it takes a +1. Well, the whole thing is going to equal to 0, just like the last one, because it's a molecule. So we have the whole thing equaling to 0. We have a +1 for each hydrogen. There's 6 of them, so that's a +6. And the carbons are unknown, which we call that X, except we have 2 carbons. You don't find the oxidation number for the sum of the 2. You want to find it for each one. So if we end up fixing this up in terms of algebra, we have 2x equals to -6. Divide 2, x equals to -3. So this is a -3 oxidation state for carbon. All right. Even though this is the hydrogen on the right side, this is not a metal. This is not a metal hydride. This is the regular old hydrogen, so it takes a +1. It's a +1 3 times, so that's a +3 total. It's a molecule with no charge, so these will add up to be 0. And then the phosphorus, we have no idea. It takes multiple different oxidation states. So we call it X. Well, solve for X, and you're going to have a -3. A few more. We have some polyatomic ions and an ionic compound. Well, this guy, I'm pretty sure is going to add up to be a -2 because that's what the charge is. So we're going to sit down and put down -2. So this is oxalate. We know that the oxygens are a -2 each because oxygens, unless it's by itself, which is 0, or peroxide, which is -1, pretty much is going to be -2. Well, we have 4 of these that take a -2, so that's a -8 all day. And then we have 2 carbons that we don't know what they are, so that's 2 unknowns, right? So then we are going to isolate for it. We add 8 to both sides. Do my little algebra here. I got 2x equals to a +6. Then divide by 2, divide by 2, and then x equals to +3. So I will have a -2 for the oxygen and a +3 for the carbon. All right, the nitrate. Well, the nitrate equals to -1 because that's what the charge is. The oxygens are -2. That's what they usually are. But there's 3 of them. So -2 and -2 and -2 is -6. And then the nitrogen is don't know what it is, so we call it X. Once we solve for X, equals to a plus 5. We know that nitrogen's a plus 5. The last one, I need to make a little room for this. Maybe I'll just whack it off here. This is an ionic compound. You have the aluminum, you have the phosphate. We can do them separate, we can do them all together. The charge for the anything is right there. And of course, what do you see right there? Nothing. You don't see anything up there because ionic compounds overall will have a 0 charge. Now, this is an ionic compound, so what is the charge for aluminum? The charge for aluminum is a plus 3, a 3 plus. So we know that that's going to be plus 3. The charge is a 3 plus. That means the oxidation number is a plus 3. If you broke this apart, you would have aluminum as a 3 plus, and then phosphate as a 3 minus. So just like our second rule, if you have something, a monoatomic ion, then the charge is the oxidation state. Okay, keep going here. We're going to have the whole thing equals to 0. We know the aluminum's a plus 3. We know that the oxygens are minus 2 each. Well, minus 2 4 times is minus 8. And we know that the phosphorus is unknown, so we call that X. So we're going to have X minus 5 equals to 0, so X equals to plus 5. So the phosphorus equals to a plus 5, and the oxygen equals to a minus 2. Finally, the difference between an oxidation state and an oxidation number. Most people don't really care about the difference, but there is an actual difference. So we typically would call SO3, this molecule, not the ion, the molecule, we typically call it sulfur trioxide. You could also call it sulfur 6 oxide because the 6 is going to be an oxidation number. And if you had an S and an O, and this was a plus 6, and these are minus 2 each, how many would you need to have in order for it to equal to 0? And the answer is you would need 3 of them. So that's where they get the sulfur 6 oxide. So the sulfur 6 right there is the oxidation number. The plus 6 over here is going to be the oxidation state. It is a little more complicated than that, but for our purposes, that will do just fine. Hope you enjoyed this video.